Okay, so today we're going to talk about free body diagrams. Now, free body diagrams are really important in physics. This is how we show forces and how we can actually calculate things with Newton's second law, which we're going to talk about next week. So, arrows in free body diagrams symbolize those forces. And what happens is that we have arrows that start at the object and point in the direction that the force acts. So a lot of the time people will actually mess this up when they start learning how to do free body diagrams. Remember, they start at the object and come out from the object. And you'll see that in the examples that we do today. So the steps here, number one, we want to identify the object we're drawing a free body diagram for. We're going to identify the forces acting on that object. Number three, we're going to draw a box or a dot representing the object. I personally prefer the box. I think it gives me more room to draw arrows and label my forces and things like that. So that's my personal preference. Number four, we're then going to draw the forces as arrows that start at the object and are pointed in the direction of the force. And then number five, we're going to label the force vectors. So for number four, going back to that, it is really important that when we draw these arrows, that if we have a large force, it's a long arrow. So the magnitude of the force is denoted by the length of the arrow. And then for number five, it is very important that we actually label those vectors. And on the next slide, we're actually going to talk about the different types of forces, but we don't want to just leave blank arrows on our free body diagram. You actually want to label those force vectors. So talking about some types of forces, the first and foremost, like most important force that's always going to be present when we're on the earth is the force of gravity. So this is going to go on every single one of your free body diagrams because we're always talking about something that is on the earth. So this is the force that keeps you on the surface of the earth, and it's always going to be directed toward the center of the earth, so straight down in your free body diagram. The normal force, this is a supportive resting force is how I like to describe it. It's directed perpendicular to the surface that the object is resting on. So for example, if I have a book sitting on a table, we have the force of gravity down, and then the normal force is upward. Now, the normal force is the force of the table holding the book up. It's that supportive resting force of the table. We just call it the normal force because number one, it can be anything, the supportive resting force. It can be the table, it can be the ground. So we want to make it kind of general. And also normal, it was the name for a 90-degree angle back in the day. So it was the old 90-degree angle name was the normal angle. So that's why we call it a normal force, because it is 90 degrees to that surface that is providing the supportive force. So that's why it's called a normal force. The applied force is the force that's applied by another object. This could be like a kick to a soccer ball, a throw to a football, a push, a pull, anything like that. We call it an applied force. The tension force is whenever we have something like a rope or a string or a wire or a cable involved. So we'll do some examples with elevators, and we know that elevators can be pulled up by the elevator cable. So we'll call that the tension force. Friction force is a resistive force due to friction. It's always directed opposite the object's motion or intended motion. So that's why it's a resistive force directed opposite the motion. And then air resistance is also a resistive force, so it's also going to be directed opposite the motion. And this is when something's flying through the air or falling, so like a skydiver, they're falling downward and the air resistance force will be upward. Now there's some other types of forces also, but the ones that we've talked about so far are the ones that we're mainly going to be focusing on in this class, but there's some other types are like the buoyant force, the magnetic force, the electrical force, the spring force, and so on and so forth. All right, so let's get into some examples. Our example number one is going to be a free body diagram of a book sitting on a table. Now, we already kind of talked about this, but let's go over it one more time. So here's my book. We know this book is on the earth, so therefore we have the force of gravity acting on that book, holding it down on the surface of the earth. So that force of gravity vector is going to come from the book and in the direction of the force. So the force of gravity is pulling that book down, holding it on the surface of the earth. Now I'm going to label that force F sub G for force of gravity. Now we know that this book is not falling down. Okay, so it's supported by the table. And that upwards force of the table, remember we call that the normal force. Okay, so I have an upwards force and I'm going to label that F sub N for normal force. And this is our free body diagram of a book sitting on a table. Now we're going to get into balanced and unbalanced forces later in this lecture, but here my forces are balanced, which means I don't have an acceleration. And here in this case, the book is at rest. Example number 2, we have a free body diagram of a soccer ball being kicked across the grass. So here's my soccer ball. I know it's a very beautiful soccer ball. Now again, this soccer ball is on the earth. So what's the first force that we draw? Yes, you are correct. We draw the force of gravity. So downward force, force of gravity. Now that soccer ball is on the grass, so the grass is providing an upward supportive force that we call the normal force. And then the soccer ball is being kicked. So I'll say that it's being kicked to the right. So I'm going to direct a force to the right. And then when we have a force that is applied like this, we call that the applied force. I like to label that F sub A. Now, if the soccer ball was moving here, we might also put a friction force and we would direct that to the left. But in this case, we're just going to keep it simple and say that the soccer ball is just starting to be kicked. So we just have an applied force. All right, example number 3, we want to draw a free body diagram of a baseball falling towards the ground, both without and with air resistance. So we'll first draw the free body diagram without air resistance. So here's my baseball. Again, beautiful baseball. Now the baseball's on the earth, so the first force that I'm going to draw is the force of gravity downward, because that's what is pulling that baseball towards the ground, causing it to fall towards the ground. Now, I'm doing this without air resistance, and a lot of the time I will tell you guys to ignore air resistance. We kind of in physics class, we like to say that this is a theoretical world without air resistance, without friction. So obviously in the real world, there is air resistance, there is friction and things like that. But sometimes we tell you to ignore it. In this case, we're ignoring it. So this baseball is falling towards the ground. We have our force of gravity. There's no air resistance. Are there any forces acting on this object? There are not any other forces acting on the object. Now, we don't have the baseball resting on anything, right? It's falling through the air. So that means there's no other forces. This is our free body diagram. All right, we're done. All right, now let's draw with air resistance. So again, here's our baseball. We have the force of gravity, which is causing it to fall towards the ground. And now we have air resistance. So which direction do we put air resistance in? We put air resistance upwards. So I'm actually going to draw a smaller arrow upwards, and I'm going to label that F sub air for the air resistance. The reason I like to spell out air here is because I already have an F sub A. That's my applied force. So I want to make sure that I'm making those different so I don't get confused. Now, the reason I drew this smaller than the force of gravity is because I wanted my baseball to be accelerating toward the ground. Now, air resistance could be the same size as the force of gravity. That would mean that we have hit terminal velocity, which is a constant velocity. All right, example number 4, we want to draw a free body diagram of a football at the top of its parabolic trajectory. So remember, a football at the top of its parabolic trajectory, we're talking about projectile motion here. So the quarterback has thrown the football, it's going downfield to the wide receiver, and hopefully they catch it for a touchdown. So it's at the very top of that parabolic trajectory. All right, so at the very top of the parabolic trajectory, here's my football. I know, it's very beautiful. Again, this football is on the earth, so I have my force of gravity downward. Now, if I have this football at the top of its parabolic trajectory, again, we're going to ignore air resistance here and just say that air resistance doesn't exist here. Are there any other forces acting on that football? There are actually no other forces acting on that football at the top of the parabolic trajectory. I know what you're thinking. You're like, Mrs. Stewart, but it's moving to the right. Like, it's moving downfield. How could there be no other forces acting on it? Now remember that quarterback has already thrown it. It already left his hands. So there's no other forces that are causing it to go forward when it's at the top of that parabolic trajectory. The only force acting on this football is the force of gravity pulling it down towards the ground, which is why it makes that parabola shape. Okay? Remember, in free body diagrams, we're drawing forces. We're not drawing the velocity vector here, okay? So we don't draw any arrow to the right, even though it's moving to the right. I know it's super, super weird, but that's how this is drawn. All right, so let's talk a little bit about balanced and unbalanced forces. So if we look at these two drawings right here, the one on the top, we have 300 newtons of force to the right, 300 newtons of force to the left. Are those balanced forces or unbalanced forces? Yes, you're right, they're balanced. So here we have forces that are balanced. The rightward forces equal the leftward forces. So nothing's gonna happen, right? Those people doing tug of war are not going to move at all. Now, what about the ones on the bottom? We have 400 newtons to the left, 300 newtons to the right. Are those balanced or unbalanced? They're unbalanced, right? We have more force going to the left than we have going to the right. So here forces are not balanced. The rightward forces are not equal to the leftward forces. So if I asked you, if we look at the bottom picture here, what is the total force, the overall force, what we call the net force? What's our net force here on the bottom? Our net force is actually 100 newtons. Okay, so what we do here is we have 400 newtons, that's going one direction, and then I'm actually going to subtract this because this 300 newtons, that's taking away from the 400 newtons here, okay? So 400 minus 300, I get a net force of 100 newtons, and what's the direction of our net force? You're right, it's to the left. Good. All right, so these are balanced forces here, unbalanced forces here. So with balanced and unbalanced forces occur when the forces that point in opposite directions are the same, such as when a book is sitting on a table. So that's this case right here, and we already talked about this. This book is at rest. We have the force of gravity going down, the normal force up. Those forces are balanced, and this book is at rest. All right? Balanced forces mean no acceleration. We already talked about this, right? We talked about this with Newton's first law. An object at rest will stay at rest. An object in motion will stay in motion unless acted upon by an unbalanced force. So if we have no unbalanced forces, this object's going to stay at rest, and this object's going to stay in motion. So this is what Newton's first law is saying. Now remember, this doesn't mean we have no velocity when we have balanced forces. It just means we have no acceleration. Constant velocity is also no acceleration. So that's this example right here. If you put your foot on the gas in a car and that engine is going to be pushing forward with a force of 7 newtons, you might still have a resistive force of 7 newtons due to friction and other things within the car and outside the car and things like that. So if those forces are balanced, it doesn't mean this car is not going to move. It just means that it's not going to have an acceleration. Okay, so it could still be moving at a constant velocity. Unbalanced forces occur when the forces that point in opposite directions are different. Now, when they're different, there will be a resulting acceleration in the same direction as the net or overall force. So some examples here, we already talked about tug of war, but again, if I have 50 newtons to the left and then 30 newtons to the right, where would our net force be pointed? It would be pointed to the left, right? This force is bigger than this force. Now, what would the magnitude of our net force be here? It would be 50 minus 30, which is 20 newtons. So our net force here would be 20 newtons to the left, and therefore they would accelerate to the left. Now in this case down here, I have 4 newtons plus 4 newtons to the right, so 8 newtons total to the right, and then 3 newtons to the left. So here the net force would be 8 minus 3, which is 5, so 5 newtons to the right. Okay, so therefore we would have an acceleration to the right because of that 5 Newton net force to the right. And then last but not least, I have a space shuttle here. We have 300 newtons of thrust upwards from the rocket engine. The weight of the space shuttle, or the force of gravity, those are interchangeable terms. I'll talk about that more when we talk about Newton's second law. So this is 100 newtons downward. So 300 minus 100 is 200 newtons of net force, and it's directed upwards. So we have an acceleration upwards here. Let's do some more examples with balanced and unbalanced forces and free body diagrams. So example number 5, we want to draw a free body diagram of an elevator accelerating upward. Now remember, we have an acceleration when we have an unbalanced force in that direction. So this means that our net unbalanced force has to be directed upward. So here's my elevator. Again, I know that this elevator is on the earth, so we are going to draw our force of gravity first. So an arrow downward, we have our force of gravity. Now again, this elevator is accelerating upward, so I know that the net unbalanced force has to be up, which means that the upward force has to be bigger than the downward force. So I'm going to draw a longer arrow upward, and then I'm going to label that with the correct force vector term. Now this is an elevator, and I know that elevator cables pull those elevators up and lower them down. So this, I'm going to label this with the force of tension. And there's our free body diagram for this example. All right, example number 6, we're going to draw a free body diagram of an elevator moving upward at a constant velocity. So here I have my elevator. Again, this elevator is on the earth, so I have the force of gravity downward. Now this term constant velocity, remember, Newton's first law says an object at rest stays at rest, an object in motion stays in motion. So this object is in motion at constant velocity. So because we have no acceleration here, we have no unbalanced force, which means that the upward force has to equal the downward force, and we have balanced forces. So I am going to draw a force vector the same size as the force of gravity, and again, this is the tension force upward because we know that it's the elevator cable that's causing that motion. Now notice how this elevator, it says it's moving upward, but this could be the same free body diagram for an elevator moving downward at constant velocity. Because we have balanced forces, we have a constant velocity, all right? And that is very important to remember. All right, this one's a really tricky one. So we have example number 7, draw a free body diagram of an elevator moving upward, reaching the top floor of a building and slowing down. So slowing down, we talked about this before when we talked about velocity and acceleration. When an object is slowing down, it's because the velocity and the acceleration have opposite signs. So the velocity is directed upward, which means that the acceleration has to be directed downward. All right? So when something's slowing down, the velocity and the acceleration are in opposite directions. The velocity is positive and the acceleration is negative. So again, here's my elevator. I know that this elevator is on the earth. So first and foremost, we're going to draw the force of gravity downward. And then I know the elevator is moving upward. So the velocity will say that's up and it's a positive velocity upward, but it's slowing down, which means the acceleration is negative, which means the acceleration is directed downward, which tells me that the downward force has to be bigger than the upward force because the acceleration is directed in the same direction as the unbalanced force. So therefore, I draw my tension force upward, and I draw that arrow smaller than the force of gravity. And that's my final free body diagram. I know that this example, it's very, very tricky, all right? So if you're confused about that, try watching this part over again and really thinking about it really hard, okay? You're welcome to always email me too if you have questions. All right, example number 8, we're gonna draw a free body diagram of a soccer ball moving to the right and slowing down to a stop. All right, so this is kind of like the other example, but it's a little bit easier to wrap your head around, okay? So again, we have our soccer ball. That's a beautiful soccer ball right there. The soccer ball is on the earth. So again, we're going to draw in our force of gravity on our free body diagram. So I have a downward arrow, that's my force of gravity. Now the soccer ball is on the ground, so it has the supportive force of the ground upward on that soccer ball. And we're gonna call that, again, the normal force. Now this soccer ball is moving to the right, but it's slowing down to a stop. So what is the force that's slowing the soccer ball down? You're right, it's friction. Now, what is the direction of this resistive force of friction? It's to the left. All right, remember, friction always acts to oppose the motion of the object. So since the soccer ball is moving to the right, that means friction is to the left. And I label my force of friction F sub FR like this. Now, again, let's talk about the direction of velocity and the direction of acceleration when you're slowing down. Remember, velocity is to the right. And then when we're slowing down, that means acceleration is directed opposite. And therefore, the unbalanced force is directed opposite. All right, notice how our unbalanced force is to the left. Our friction force is opposite that motion, and therefore we're slowing down. Our acceleration is directed to the left as well. All right, example number 9, we're going to draw a free body diagram of a hockey puck being pushed across frictionless ice. So here's our hockey puck. That hockey puck is on the earth, so we have the force of gravity downward. The hockey puck is being supported upward by the ice, so we have an upwards normal force from the ice, and then it's being pushed across frictionless ice. Now I'm going to say that it's being pushed to the right, so I have my applied force to the right, and then the ice is frictionless, so I'm not going to draw friction in here because it's frictionless. So that's our free body diagram for this example. Now for number 10, we're going to draw a free body diagram of that hockey puck after the push stops, and it's now sliding at constant velocity across frictionless ice. So again, here's our hockey puck. It's on the earth, so we have force of gravity down. It's being supported. It has an upwards force from the ice supporting that hockey puck. So we have a normal force upward. And then it says it's after the push stops, which means that we don't have an applied force anymore. And it's sliding at constant velocity across frictionless ice. So there's no friction. So no applied force, no friction, and it's at constant velocity. Now, what does constant velocity mean? It means there's no acceleration, which means the forces are balanced. Now, in this picture right here, are the forces balanced? Yes, they are. Now, you might be thinking, but it's moving to the right. Shouldn't we be drawing an arrow to the right? We should not, okay? This is our final free body diagram for this example. I know it looks really weird because it looks like the example of the book just sitting on the table, all right? But since we have no friction, we can't put that arrow in there because it's frictionless. So there's no force of friction. The push has stopped also, so there's no applied force. So yes, I know this is really weird, but remember, it still can be moving at constant velocity when forces are balanced, even when there's no forces at all. Galileo said, an object in motion stays in motion unless acted upon by an unbalanced force. This is the example of the object in motion staying in motion, all right? And theoretically, if there was no friction, it would just stay in motion and slide forever and ever and ever if there's no unbalanced forces. But of course, this is not a total theoretical world. So I hope you guys found this helpful. If you have any other questions, please feel free to email me. Come to office hours on Friday from 10 to 11 a.m. I will be hanging out ready to answer your questions, all right? So I will see you next time.